everybody. Today we're going to be discussing exponential functions, and what these do is simply elaborate upon the ideas we learned from composition and inverse functions. So ideas from those sections will be coming up in the next two sections. So exponential functions, well, you all know what an exponent represents or is. It's a base to a power. And so I wanted to start off this homework set, this lecture, by talking about some of the laws of exponents, and I do have them in the notes. I also wrote them down again here, as well as a few examples that we're going to go through and just kind of mix and match which ones use which. 2 to the negative 3, for example. So if you see any negative exponents, then you notice the rule down here at the bottom. What that represents is any number that has a negative exponent. Well, as you see here, you take that expression, you can bring it to the bottom underneath 1, and notice the only difference is that the minus sign is now gone. So the minus sign is gone. We're going to do the same exact thing here. So all this represents is 1 over 2 to the third power. Notice we put everything under 1, and the negative is gone. The cost of reciprocating the value is taking away the minus sign. And from here, we can go ahead and solve this. 1 over 2 to the third power, well, 2 to the third power is just 8. So 1 over 8 would be our final answer in this problem. So we move on to 5 to the negative 1 raised to the negative 2. And what this rule is correlating with is what happens when you have an exponential function raised to an exponent of its own. And that actually matches up with the rule right here. And it says if you have an exponential raised to a power, then you multiply the exponents together. So we're going to do precisely that. So that rule says that we will multiply the two exponents together. So notice the negative 1, the negative 2, and that product is simply 5, well, negative 1 times negative 2 is positive 2. And we all know what 5 squared is, it's 25. From here, we utilize another rule. So here we have two exponents being multiplied together. And, well, one thing we could utilize is you could throw it all in your calculator if you wanted. I mean, technically for any of these problems you could, but it doesn't generalize as well as these properties, as we'll see throughout this section. And so a problem like this, that would correlate with the first property up here, where if we multiply two exponents together and they have the same base, then notice the same base carries over. So notice this A and that A will become 1A, or in this problem, the two 9's merge together to give us 1 9. And from here, it simply says add the exponents together. So not multiply, that's this rule. It's add the exponents together. So that would be negative 5 plus 4 in the exponent. Now we can go ahead and simplify that. Negative 5 plus 4 is negative 1. 9 to the negative 1, well, that reduces down to this rule over here. That's simply 1 over 9. Technically 9 to the first power, but that's understood to be 9. This would be our answer for the third part. So finally, we have 27 to the 2/3. Now again, you could throw this in your calculator. This does actually use a rule that I did not write up here. From what I've noticed, it doesn't show up too much in the section, so I didn't want to emphasize it as much. But the rule is the denominator of the exponent will act as a root. In fact, we might have gone over this before. So this would tell us that we have the third root of 27. And the reason why we have a third root is simply by virtue of what it means to be a denominator in the exponent. And then what happens to that 2? Well, it goes on the outside. The third root of 27, that is 3. And we conclude with 9 for this problem. But mainly, I wanted to focus on the rules that correspond to these. And if you did see this one, I wanted you to be aware of how to do this one. And that would conclude this problem. So now that we've discussed just some general properties of exponentials, now we're going to move on to the basis of the section, exponential functions. And an exponential function, so I wrote it down all here, that there is a general form very similar to the y equals mx plus b. That's one of those formulas you just have to know. This is another one very similar to that. And just like how y equals mx plus b has two constants, the m and the b, the slope and y-intercept, this one also has two constants, which means that's two things that we may need to solve for if we're constructing such functions. And I also provided a new parent function. So remember that we had a list of parent functions a few sections back. The section was called Library of Functions, and I'm adding another shape to it. So this is the shape, the parent function for an exponential function. I also have this in the notes, and so we will be referencing this quite a bit. I'll go ahead and just leave it up on the board because we will be referencing this throughout the section. So please make sure you have that as a quick reference throughout the section and the corresponding homework. We will move on to example 2 in the notes that do want us to determine, so what they're giving us, each row for each one of these is an ordered pair. They're giving us a bunch of points on a graph, and what they want us to do is determine whether these points go in a linear fashion. So if you were to plot all the points, do they go in a linear fashion, or will all the points go in a shape that corresponds to this? And that's what we get to find out in this problem. So the first problem, I actually want to look at problem 2 first, because we actually did this type of problem before in the section on linear functions. And so when we determine if a trend is linear or not, so that's the first question. It says, is this linear, exponential, or neither? And so what we did was we determined the differences between the y values. So what's the difference between 3 and 8? So that's a difference of positive 5 when we go in this direction. If we go from 8 to 13, that's a difference of, well, guess what, 5. And if you keep going, you're going to keep getting 5. So the fact that we get the same number every time tells us that the slope is 5, because we get the same number as we increment from each y value. So that tells us, well, that tells us we have a linear function. And so how do linear functions look? Well, it's y equals mx plus b. So instead of mx plus b, we know that the m is 5. But we still don't know what the y-intercept is. However, we actually do in this problem. Remember, the y-intercept is when the x value is 0. Notice in this row right here, the x value is 0, the immediate corresponding y value is 8. So that immediately tells us our y-intercept right there. They give it to us actually. So now we can go ahead and update this as 5x plus 8, where the 5 is the constant trend, and the fact that it's constant means that this is linear, and we get the 8 from the y-intercept. So this would actually be our answer for this part. But over here, you may notice, if you were to consider the differences between the y values, so I don't know offhand what the difference between 4 and 4/3 is, but The difference between 4 and 12, that seems to be 8. The difference between 12 and 36, 24. So that already tells us if we were to consider that same option of determining the displacements here, that would be 8. This would be 24. And notice we don't get the same number. And simply by virtue of not getting the same number, we can determine that this is not linear. So it's not linear, so we have to try something else now. So now we ask, is this exponential? And so what does it mean to be exponential? Well, it has to follow this formula. So that's the formula we're going to start off with. And very similar for this problem where we had to figure out M and B. Over here we need to figure out A and C, or C and A, whichever order. So what I would suggest first is, well, throughout this problem we're going to be utilizing test points. So they do give us these points, and we can utilize these to help us determine our constants. The first point I want to utilize is actually the second row here. The reason why is because we have two variables, and if we plug in 0 for x and 4 for y, the 0 for x will help us get rid of that a variable, and we can solve for c. And then after we solve for c, we can go ahead and solve for a. So let's go ahead and do that first. So we'll start off with, we're going to use test points. So remember, test points, it's a temporary substitution that allows us to find things. But once we use the test points, we have to revert back. So the test point we're going to use is 0, 4, which is coming from the second row right here. And so that tells us plug in 4 for y. C and A are still constants, we don't know what they are. And x here is 0. And so now, what we get from this, well, anything to the 0 power is 1. That's why this expression right here goes to 1. Anything raised to the 0 power is 1. And now we get that 4 is equal to c. And so now that we get that, we can go ahead and, remember, this was a test point. This was just a temporary set of values that we plug in to figure out a constant. So now we can update our starting function to f of x is equal to, well, c is 4. So now 4 times a to the x. But we're not done, because we need to figure out a. And we can figure out a by, well, utilizing any other point. Just any one. I'm going to pick this one because that one's got a fraction, and I'd like to avoid that one. So I'm going to pick the third row. So this is again going to be another test point that I utilize here. So it's the same idea as before. So the test point I'm going to use, like I said, I'm picking the third row. And that gives us an x value and a y value, a temporary x and y, that will help us solve for the unknown value. So 1 here is x and 12 is y. And so now when we plug in 12 for y and 1 for x, we get precisely this expression here. So now it's just a matter of dividing both sides by 4 to get a by itself. And once we divide both sides by 4, we simply get that a is 3. But our answer is not a is 3. It does help, but remember, test point means we have to revert back to what we started with. So we started with this, and so finally, after all of the scratch work, we can plug in 3 for a. And this will actually be our answer. So we can conclude that this trend for problem 1 here is exponential, and that its function is 4 times 3 raised to the x. And when you put this in my math lab, the way you can denote a dot, you can use an asterisk on your keyboard. So besides for that, that would conclude this problem. So now what we're going to do is, instead of looking at exponential functions algebraically, let's go ahead and start familiarizing ourselves with the parent function and how we can use that to identify transformations and associate those to corresponding functions, such as in example 3, which it'll want us to do exactly that. So you may notice for example 3, it says determine the corresponding exponential function, and then it gives you a list of 8. And the idea that I suggest is we'll go through them by process of elimination. In fact, there's one thing we can determine right away to help us narrow this down tenfold. So we'll start off with problem 1 here. And so this is an exponential function. The problem says match this to the corresponding function. And so one thing to note about this over here, because we're going to base this in relation to the parent function. So this shape here, this is the traditional parent function. In particular, this is, we can view this exactly as just a to the x, where a is just some base. It could be 4 or 3. In this problem, if you look at all the answer choices, they have a bunch of 4s, which means that a would be 4 in this case. So how we want to compare this is see how this shape compares to this shape. What happens? What kind of transformation happens? And we see that there is a difference in the direction the shape is going. It originally starts off over here going upwards, and now over here it's flipped. So this flip is important to identify. So there's a reflection in particular. There is a reflection about the y-axis here. That's the comparison between this one to this one. How do you go from here to here? You reflect about the y-axis. And so if you can make that observation, well, let's remember, what does it mean to reflect about the y-axis? How does that translate algebraically? So try to think back to transformations, because what that represents, when you reflect about the y-axis, you make the x negative. So a reflection about the y-axis, so a reflection about the y-axis you make x negative x. So let's go ahead and look at our list of functions here. So answer choice A, the x variable is positive, so A is out. All the x's have to have a negative in front of them. So A is out, so technically B is good. So I'll start to write down the ones that seem to be okay so far. So B is okay. Because there's a negative in front of the x. C is out. D is okay. And so we keep going. E is out. F is out. G is actually okay. There's still a negative in front of the x for G here. So, and H is also out because the negative is not in front of the x variable directly. So we're down to these 3. And so now the question is, well, how do we narrow it down from there? So what my graph doesn't show is there are grid lines on your notes. So the grid lines will help you determine actually one or more points on the graph. It may be hard to see, but for this graph right here, you actually get 2 points. One of them is this y-intercept here, and you can use the orientation of the grid lines to tell you that this is 0, 1, and you actually get another point. In fact, let me reference, it should be -1, 4. It's hard to see it here. However, on the notes, this is much easier to determine because of the grid lines. And so what I would recommend is, well, the idea of test points. We can plug in any one of these points into each one of these functions, and what the points tell us is that if we plug in 0 for x, for example, so if I choose this test point, if I plug in 0 for x, I better get 1 for y. So let's go ahead and test out that theory for each one of these. If I plug in 0 for x, so we're going to use this test point, then we better get 1 for y. So let's see how that works out. So if we plug in 0, then if we plug in 0 for x, then we get 4 to the -0. Of course, -0 is just 0, and 4 to the 0 is 1. And we got 1, which does correspond to this 1. So we're good so far. So this is, so far, doesn't mean it's the right answer. It just means that we don't narrow it out. We don't get rid of it quite yet. So far this is good. Let's move on to answer choice D here. If we plug in, it's the same idea. If we plug in 0 for x, we better get a 1 for y, because the ordered pair tells us we have to get that. So if we do the same process, we're actually going to get -1. The only reason we get a -1, we still get a 1 from before, but there's a negative waiting for us. So that -1 completely contradicts the y value we were supposed to get. And so that means answer choice B is gone. Let's go over here to G now. It's the same idea. And over here, you see that we get 4, because in the exponent, it's 1 minus 0, which is 1. 4 raised to the first power is just 4. Again, the ordered pair told us that we were supposed to get 1, but we got 4, which means G is out. And simply by virtue of that, we can conclude that B is the correct function that matches this graph here. And so from here, we can apply a very similar thought process to problem 2 over here. So let's make some room here. So we can start off by comparing this with the parent function. And so this one might be, it may or may not be a little bit trickier. There is a reflection. That's something we can determine. Something else to notice is that the asymptote is not in the same spot anymore, but we can figure that out later. Let's just focus on the shape. So what's the shape telling us here? Before, the shape's going upwards like this, and now that exact shape seems to be reflected. In particular, it seems to be reflected about the x-axis. So if something reflects about the x-axis, so not the y-axis, so a reflection about the x-axis, so what I'm going to put is that y becomes negative y. In other words, this means the function, you put a negative in front of the whole function. So that's what this refers to. So we're going to go through each one of our functions like we did before and simply write down the ones that satisfy this idea. And I'll go ahead and isolate this from our previous problem here. So let's go through one by one and see which functions have a negative in front of, well, the whole function. So A is out, there's no negative. B, the negative's in front of the variable, not in front of the function, so B is out. C is okay, so we start off with C. So C is okay so far. D is also okay. And finally, there should be one more. So notice in part H, this one may be kind of difficult to see, but part H actually satisfies this as well. And I think I'm going to run out of room over here. I'm going to put H down over here. So I have them a little bit mixed up. But here's the three candidates that we have left. So here I said there needs to be a negative in front of the whole function. The negative is referring to the 4x here, because the 4x tells us what the shape is going to look like. It's the power function in essence. And the 1 here is insignificant. So that's one way you can think about it. So we now have these three, and the idea, well, just like we did in the last problem, let's go ahead and find some test points. So one of them is pretty obvious. It's the origin. And I'm pretty sure there's another point here that we can utilize. Let's go ahead and start off with the origin. So the origin is 0, 0. And we'll go ahead and use that as a test point. We'll compare that to every single function, see if it works or not. Let's start off, I guess, we'll start off with H here. There's no order in which you have to test these in. So here we're testing the point 0, 0. What this says is, if we plug in 0 for x, we better get 0 for y. So let's go ahead and figure that out for each one of these. And this x should be an exponent. So that should be an exponent. So that would be 4 raised to the 0. Anything raised to the 0 is 1. 1 minus 1 is 0. Or you could just throw that all in your calculator at once. So this is good. This is okay. This does confirm x for 0 and y is 0. So this one's good so far. Let's move on to part C here. Same idea. So here, it's not negative 4 to the 0, it's 4 to the 0, and there's a negative out front. So the way we look at this is 4 raised to the 0 power. Anything raised to the 0 is 1. So that's why this would be negative 1. But despite how you do it, the point up here says y is supposed to equal 0. And we just found y is negative 1. So simply by virtue of that, C is eliminated. And we move on to choice D here. So same idea, we plug in 0 for x, we see if we get y as an output or not. So we have negative 0, which is just 0. That's 4 raised to the 0, which is 1, and there's a negative in front. So this is also negative 1. Again, we were supposed to get 0. We did not get 0, so D is out. And that tells us that H would be the correct answer here. So that would be the function that corresponds to the graph here. And that would conclude this problem. So we're going to be elaborate on a little bit more on what we did just before, but this will require us to construct the transformation rather than be given a transformation and determine the corresponding function. So in particular, we have a problem here, and do tell us to graph the function using transformations. Now, you will see an interactive graph, and when you go to interact with this graph, you're going to see maybe one or two functions in the tool palette, and if you run your cursor over one of them, it'll say the exponential tool. Since we're in exponential functions, we're going to be using that shape. It'll look a lot like this, and it will, once you click anywhere on the graph, it'll bring up that familiar box that we've been using where it says the vertical stretch compression, the vertical shift, the horizontal shift, and there's, I think, boxes for the reflections. There's also going to be a new option that says the base. And what the base represents, so with any exponent, the number that has an exponent corresponding to it would be considered the base. So whatever number has an exponent is a base. In this problem right here, 5 would be considered the base because 5 has an exponent. It's right here. So let's go ahead and jot that down. So this will be stuff that you would fit into your whatever they call it, the graphing tool. So the base would be 5. It might even have this for you defaulted to 5. It might already say 5. If not, just change it to 5. Also, we need to determine any other transformations that may be happening. So this 5 here does not tell us a vertical stretch or compression. It does not tell us that. The 5 is the base, and it has a different function to it. So additionally, we want to see for any shifting. So we do have a shift up of 3. So remember, anytime you add a number to a function, that tells us we go up 3. Oops. So this is up 3. That's what this number tells us here. And then the x minus 1, remember, that's the opposite. We go to the right one when it's minus 1. And I can't remember which one's which, if that's I can't remember if that corresponds to horizontal or vertical shifting, but if you mess around with the sliders, it'll show the graph going up, down, left, or right. I'll go ahead and graph it out here. You won't need to know how to generate this for the homework. However, I do have it written out here. So I think it's 1, 2, 3, 4. 1, 2, 3, 4. And so it seems to be your graph should look something like what I'm about to draw out now, once you're done. It should look a lot like this. And if you compare that to, so notice the shape is the same because there's no reflections. And also that point, that 0, 1, that gets shifted up 3 and to the right 1. So notice it goes up 3. So this value for y was originally 1. That y is now 4. So right 1, 0 becomes the 1, up 3, that's how you get 4 here. You don't need to know this for the homework necessarily. It may be helpful for the test coming up, but you should have a graph that looks like this nonetheless. And so from here, it'll also ask us to determine the domain, the range, horizontal asymptote, and the y-intercept. So what may be convenient about this section? So as I mentioned in the notes, every exponential function has an all-real domain. Every domain for an exponential function, it's always negative infinity to positive infinity. That's for every single exponential function. And what we can do to verify that with the graph, to the left, we go on forever. To the right, we also go on without any restriction. So that graph verifies it in this situation, that the domain's all reals. You may notice that the range, though, will not be all real numbers. Because if we try to go down forever, well, we hit this barrier. And normally that barrier is going to give us an idea of how to represent the range. So let's try the idea that we've been using. So the furthest down we can go, we seem to be stuck by this barrier. So where is this barrier at exactly? This barrier seems to be, so originally, the barrier is at, they tell us, y is 0. But because we went up 3, that tells us that the barrier is now at y is equal to 3. So since we went up 3, y equals 0 becomes y equals 3. So that tells us where this graph starts to really plateau at or converge towards. So the lowest point we get, we use the horizontal asymptote to represent this, but we use a parenthesis because it is in fact an asymptote. And if we try to go up forever, we succeed. There's no asymptotes that direction. So that would be infinity. And so this would be the range. And so we move on. Well, I just mentioned the horizontal asymptote. Now we're going to represent it formally. So I actually wrote it down right here. So sometimes they'll have y equals for you, and you just put the number, or sometimes they'll ask for an equation. I'm just going to be safe and put y is equal to 3. Every exponential function has a horizontal asymptote, and the placement of the horizontal asymptote in relation to the parent function simply depends upon how much you shift up or down. Just up or down. Left or right doesn't affect the asymptote at all. So since we went up 3, the asymptote went up 3, and we conclude the horizontal asymptote with this. And finally, we need to figure out the y-intercept. So if you may notice, the y-intercept isn't quite so easy to determine here. My graph isn't drawn the best, but once it's drawn out on yours, it's still not going to be very clear what the y-intercept may be. You have to figure it out algebraically. So they do give you a function. And from this function, you can determine what the y-intercept is. Remember, the y-intercept, you gotta set x equal to 0 and solve for y. So let's go ahead and set x equal to 0 and do just that. So here, it's 3 plus 5 raised to the 0 minus 1. And so here we now get, so this is scratch work off to the side. Well, this is 3 plus 5 to the negative 1. If you try to put this in your calculator, well, it'll give you a nice decimal. But this does represent 1 over 5. And the reason I emphasize that, 0 minus 1 is negative 1. 5 to the negative 1, that's something we just learned at the beginning of this section, means you flip the base, as we did here. And so, actually, they will probably want a fraction as an answer. And to make sure you get a fraction as an answer, well, you can use your calculator. So the decimal may not be too helpful, although it may be correct. So 3 plus 1 over 5, I'm going to convert that to a fraction, and I get 16 over 5. And that would be your answer for this problem. So now we're going to look at a similar problem, but one thing to notice about this problem, they have this letter E, and well, this is actually our first time being introduced to something called Euler's number. So that's, you don't have to know what it means offhand, but if you see E, E is actually something that's very similar to pi. You know, that irrational number, it's 3.14, goes on forever. E is actually the same thing. In fact, if you look at your calculator, I'm going to mention this later on in the lecture. If you look at your calculator, on the far left-hand side of the calculator, the third button in blue, it says e raised to the x. We're going to be utilizing this later on in this section. But for now, e is just some value that we're going to simply just let happen. But I wanted all of you to be aware that this is an important number that's going to keep coming up more and more throughout the remainder of the class. So here, and in fact, E in this problem represents the base. So whenever the interactive graphing utility comes up, one of the options is the base. It might have E there for you, but if you want, you can, or if it doesn't, just put E. And you do just type in E. There's no special character for it or anything. And so also, we have a reflection, because there is a negative here in front of the X. A negative in front of the X means we reflect about the Y-axis. And then we have one more thing we need to consider. That's what to do with the 5. Because the 5 is not a base. The 5 doesn't have an exponent. So the 5 is actually the vertical stretch in this problem. So that it's actually the vertical stretch. And remember, we don't ever use the horizontal stretch. We just use the vertical stretch like we've used before. But if you go ahead and plug all of those values in, my math lab will generate the graph for you. And just to make sure I generate the graph correctly, a vertical stretch of 5 will take that initial point and, well, it will move it up 5 in essence. They may not be too clear, but when you stretch out the function, what you're doing is you're stretching out the function to a sense where it seems like that point is going up 5. Or if you plug in 0 for X, you would see that you would get 5 for Y. In any case, you would get 2, 3, 4, 5. You would get a point right here. And since there is a reflection about the Y-axis, that means that this shape will now be reflected to resemble this shape. So that shape will now look like this. And one thing I am forgetting, or I'll go ahead and add it now, the asymptote does not change. There's no shifting up or down. That's the only thing that affects the asymptote. There's no shifting up or down, so the asymptote is still here and Y is equal to 0. And so let me go ahead and draw that a little bit more nicely so we can figure out these a little bit easier. So there is a point here at 0, 5. There is a graph that is coming through like that. There we go. And so from here, we go through all the same ideas. And as I mentioned before, the domain is still all real numbers. Every exponential problem, domain is all real numbers. Again, we can look left to right to make sure. Goes to the left forever, goes to the right forever. The range, it's not as flexible, because the furthest down we go, we're restricted by this horizontal asymptote. This asymptote is happening at y is 0. So that gives us an idea for how to represent the barrier when trying to go downwards. So 0 going down, but it seems like we can go up forever. So that's to positive infinity. Horizontal asymptote, we don't shift up or down at all, so it stays as y is equal to 0. Unfortunately, the y-intercept here, just by virtue of how the problem worked out, we're able to figure out very quickly what the y-intercept is. There's no ambiguity in between grid lines. So here we can see that the y-intercept is 0, well, the point is 0, 5. The y-intercept itself will be 5. And mainly this problem was a loose introduction towards Euler's number. We're going to be looking at that a lot more as the section progresses. We'll go ahead and move on to actually solving exponential functions now. So solving, implying that we will be finding a solution set for x, we will be getting x by itself. And so I'll go ahead and start off with these two problems here. And what these are going to utilize. So what these utilize, there's actually a helpful property that says if you can get the, so remember, a base is a number that has an exponent. Over here, a 3, or the number 3 over here is a base. There's a property that says if you can get the base on the left side and the right side to be the same, then you can cancel out the bases and just have the exponents equal each other. So that might be a little bit confusing what I just said. And I'll go through a few problems to emphasize this. Because, well, the first thing is the bases on the left side and the right side. The left side, the base is 3. Well, the right side, I mean, technically 9's a base with a power of 1. However, they're not the same. It's not the same base. So we're going to force or try to rewrite the problem to where we can get both sides to have a common base. And so something you may notice, so think about 9 for a second. So 9, how could you rewrite 9? And so this is kind of the thought process we use, and we're dealing with a section on exponents. So 9 and exponents. Well, it turns out that 9 is 3 squared. And you might think, all right, cool, so what? So let's go ahead and write that fact down. So 9 is 3 squared. And you might notice, so I didn't change the problem at all. I simply rewrote 9 as 3 squared. And the reason I did that is because now the 3's here it's the same base. And remember that property that I mentioned. If you can get the same base on both sides, the bases cancel out. So over here, now the base over here is 3, base over here is 3. Since they're the same, they cancel out. And guess what? The exponents will drop down. So 3x plus 1 here is equal to 2. That's it. And now it just reduces to a linear equation. And we simply get that x is 1 over 3. And that's it. So that would be problem 1. And so there's a few of them, maybe 1 or 2 more that are like this. There is a slightly more complicated one that I wanted to talk about. And this is when fractions are involved. And so the question is, how do we get a common base when we have a bunch of fractions? Well, let's break this down a little bit. Let's look at just the numerator. So this is going to be scratch word off to the side. This is looking at just the numerator. So if this were the problem, then how would we rewrite 27 to get, well, a base of 3? Well, it turns out 27 is 3 raised to the 3rd power. So what we can go ahead and do is rewrite 27 as 3 raised to the 3rd power. And from here, well, the bases cancel and get that x is 3. Okay, well that's the numerator. Let's look at the denominator and see if we get the same thing. So here I will take the denominator, it's 2 raised to the x is equal to 8. Here I'm taking all the denominators with the exponent. Same idea, how can we rewrite 8 to have a base of 2? Well, it turns out that 8 is simply 2 to the 3rd power. Just like that. And so from here, the 2's cancel because they're the same base. We get x is 3 again. Because these two match, well, guess what our final answer is? Simply x is equal to 3. And that's it for this problem. So we can go ahead and move on to problems 3 and 4. So let's go ahead and look at 3. And this is when the law of exponents is going to come into play that we talked about at the very beginning of the section. So make sure to have that as a reference as I go through these. So now we have a problem like this. And you might see that there are, technically, if I were to say the base, in this problem, that's an ambiguous thing to say. There's 49 as a base, 7 as a base, and 2401 as a base. So we need to figure out a way to make all of those one common base. Generally, the smallest number will be the most accessible as a base. So 49, for example. How can we drop down 49 to be 7? Because 7 is the smallest of all the bases here. So 49 is simply 7 squared. So what I'm going to do is I'm replacing 49 with 7 squared, and there's still an x as an exponent. So I'm not going to just simply drop off the x. 49 is 7 squared, putting that in parentheses, and I'm bringing down the x. 7 seems to be, in simplest terms, it's already a base of 7. The 2401, well, that's definitely not 7 squared. So if you're in doubt, try to just figure out powers of 7 in your calculator. 7 raised to the 3rd power, it's 343. That's not right. What about 7 raised to the 4th power? Well, it's 2401. So 2401 here, this whole value is 7 raised to the 4th power. And there's still a 2 here. That 2 is going to go right here. So that's where the 2 is going. I haven't forgot about it. It's similarly to the x here. And from here, now this is when I mentioned having the law of exponents handy. Because now we have an exponent, an exponential expression raised to an exponent. Do you remember how the exponents here interact? They multiply. So 2 times x is just 2x. So we're utilizing that law of exponents. So times, over here, this isn't an exponent raised to the 2nd power. This is 7 raised to the x squared. So that stays. But over here, this is an exponent raised to a power, which again, the exponents multiply. It's 4 times 2 in the exponent. That's 7 to the 8. And the 8 is the 4 times 2. So you might think, okay, well, we got common bases on both sides, the left and the right side. Can we go ahead and cancel? The answer is no. We cannot cancel yet. The reason why is because the left-hand side is not just one base, it's 2 bases, and that's not good. We can't cancel until all the bases are reduced to just being 1 on both sides. The right-hand side is ready. There's only 1 base. Left-hand side, there's 2 of them, and we need to bring them together to give us 1. But you may remember another one of the properties from the law of exponents that says if we have 2 exponents being multiplied together with the same base, we can add the exponents together. So what we're doing is utilizing exactly that rule. If you have like base exponents multiplying, you can add the exponents. So 2x is here, x squared is here, and we're adding them together. Now we have a singular base on both sides, which means we can cancel out the bases. So we can cancel out the 7s and drop down everything else. So from here on the left-hand side, we now have 2x plus x squared, and on the right-hand side, it's equal to 8. And yes, we do have a quadratic. We need to put this in standard form and factor it. I won't spend too much time on that, but the modification to put this in standard form is here. Factorization seems to be x plus 4, x minus 2. And from here, we get that x is equal to negative 4 and positive 2. And it is okay that we got 2 answers. So that is okay. We can get 2 answers from these types of problems. But that is how you would do problem 3 here. And we'll go ahead and move on to problem 4, which you may notice has the e stuff again. So let's go ahead and look at that. So now we have a problem with a bunch of e values. And so for this problem, my suggestion is to just treat e as if it were the number 2 or the number 4 or something. And so what we want to do, so it's the same idea still. We're trying to get like bases on the left and the right so we can cancel them out. I do see a fraction here. And whenever I see fraction, I think about multiplying both sides by the denominator. This here is all one term, so it only gets 1 e to the 42, because this is multiplication. So over here, that means that these two would cancel, and we now get exactly this equation here, because now we've multiplied the e raised to the 42 onto the other side. Now it appears here. So we would love to cancel out the bases now. However, there's more than 1 on the left-hand side. So very similar to the previous problem, they already have common bases, so that's good. We just have to add the exponents, because that's the rule from the law of exponents. So in particular, we add the exponents, just like that. And from here, now we can get rid of the common bases. And from here, we get, well, x squared plus 42 is equal to 13x. And yes, we do get another quadratic. And so when we go ahead and figure this one out, it seems to be -6 and -7. Here we get 2 answers again, which is okay. These would be both of our answers for this problem. And that would conclude these types of solution-based problems. We're going to look at example 6 here now, which is asking for us to determine the exponential function whose graph is given here. And something you may or may not notice about this problem is actually very, very similar to that table problem we had, where each row on the table represented an ordered pair. In fact, this is the exact same problem. It's just instead of giving us that information via the rows, they just give us a graph and kind of show us the association that it has to an exponential function. And so they tell us to use these points to determine, well, they tell us that it's going to be an exponential function. And since we have that information available, we every exponential function looks like this. And so, remember what we did for the table problem. We took the value that had 0 for x, and we used that as a test point. We're going to do the same exact thing here. It's the exact same problem as the table problem. So we'll start off with the test point of 0 comma, that should be a -1. Should be a -1 there. Here we go. So the test point of 0 comma -1. And remember, this is a temporary point that we plug in for x and y respectively, and we can use that to determine one of the constants, in particular c. So it says -1 for y is now c times a raised to the 0. Just like what happened in the table-based problem. A to the 0 is 1, which leaves us with c is equal to -1. So we can now update our function to resemble that. So just like this. Or you could put a negative sign as well. So now, just like we did with the table problem, again, we will pick another point. I'll pick 1 comma -4. So I'm picking this test point. Again, it's a temporary x and y value that we choose to determine the missing value. So it says -4 for technically y. We get this here. Well, a to the first power is just a. We can multiply or divide, it doesn't matter. -1 on both sides, and we just get that a is 4. So a is +4. And from there, we can go ahead and once again update our function. We can update our function one last time to give us -4 raised to the x. Let me go ahead and put the function notation in. So just like this. And you can also put parentheses around the 4 raised to the x if you want to isolate them, if you may. Other than that, this would be your correct answer. Finally, we'll conclude this section by talking about 2 of the application problems towards the end of the homework section. And these are actually the easier of the problems throughout this section. These do work out very nicely. And so let's go ahead and start off with example 7, which I'm not going to write out in its entirety because it is an interpretation-based problem. They do give us a function for example 7, and it's p of t is equal to 100 times 0.5 raised to the t. They do give us this function, and then they say what % of patients survive 1 year after initial diagnosis. So if you were to plug in, so it does say 1 year, and we do have a t variable for time. So there's a few things going on here. We're starting off with 100 patients. This is part of the interpretation of this problem. So we start off with 100 patients. And then it says, if we plug in 1 for t, so 1 year, how many patients do we end up with after that? So we have a function here. Let's go ahead and just plug in 1 for t and see what happens. I get 50. But 50 is not the answer because it's asking for the percentage. 100 in relation to the 50, what % of that is survival? So how many people are left over? That's 50%. So that's how you would answer part A. It's 50%. So that's 100 to 50 people. So that would be the answer for part A. Part B, well, it says the same thing, but it says replace t with 2 for 2 years. So we'll go ahead and plug in 2 for t. and what you should get is 25. So we go from 100 people to 25 people. And what percent of our survival is that? So another way you can look at it, it would be 50 divided by 100 to, well, give you 50%, 25 divided by 100, that would give you 25%. And then finally, what it wants us to determine, so what percentage survive in comparison to the previous year? Well, what they're asking for is the base. The base tells us the rate in this regard. So this will be 50%. The percentage of base. And so that's pretty much this problem. And example 8, it works out really nicely. So notice there's that E thing again. And this problem is simply a way to determine if you can solve problems involving E in the calculator. So here, what part A says, well, they do give us a function. And here they give us 1 hour. Well, we do have an H variable. So what they want us to do is plug this whole expression into the calculator, just like that. And so that means you need to know how to use E in your calculator. And if you do everything correctly, I'm pressing 5, I'm pressing second on the calculator to get to the E setting. On the calculator, it'll have E with the caret and then an open parenthesis. The open parenthesis is nice because that's where we can put in the negative 0.16 or negative 0.16 times 1. Then once you plug in the 1, you can close the parenthesis. And here it says round to 2 decimal places. So round 4.26. So that would be part A right there. 10 hours is very similar. Except instead of 1, we have 10. So let's go ahead and plug that in and see what happens. And again, 2 decimal places, this is 1.01. And that would conclude, actually, the section.